Hey everyone, we are going to start the introduction of some very important notes for Chapter 2. Chapter 2 focuses on the bell curve, and we're about to get into a very important calculation we're going to need to know how to do in order to apply it to the bell curve, and that is called the z-score. So we just started talking about measuring position of a score with respect to everyone else, and we were talking about percentile. Percentile is the percent of data that you are greater than or equal to. Well, another way of measuring the position of a score with respect to everyone else is called a z-score. The z-score tells us how many standard deviations we are away from the mean, and specifically in what direction we are located with respect to the mean. So are we on the right of the mean? Are we on the left of the mean? Or are we at the mean? Are we above the mean? Are we below the mean? Or are we at the mean or the average? So think about if you are doing a test for the class, like our Chapter 1 test, you want to know how well you did compared to everyone else, right? So what is your score with respect to the class? Are you above the average, below the average, or are you at the average? So in order for you to get the standardized score or the z-score, you have to do the following formula. The formula is you take your score, which is your value, x, you take away the mean, mu, which is the class mean, mu, and you divide by the standard deviation, sigma. Okay, notice here I'm using the symbols mu and sigma instead of x bar and s because I'm assuming that these are population numbers. So mu stands for the population mean and sigma stands for the population standard deviation. Okay, so if I want to find your position with respect to everyone else, what I do is this formula, which is called standardizing your score. So think about standardized tests like SAT, ACT. Those are all called standardized tests because we're putting everyone on the same scale. And that's what we can do here with a z-score. All right, so let's now look at an example. So we saw this example in a STEM plot. Jenny scored an 86 on the test. That's her score. The class mean was 80. That's going to be mu. And the standard deviation was 6.07. That's going to be called sigma. Find and interpret her standardized score. All right, so if we want Jenny's score, we have to do the z-score formula, which is x minus mu over sigma, or her value minus the mean over the standard deviation. Okay, so she got an 86. That's going to go in place of x right here. Minus, we're going to take away the mean because we want to see how far away she is from the class mean. So if the class mean is an 80, she's above the mean because she got an 86, right? And the standard deviation for the class was 6.07. So we're going to divide this and see what we get. In the calculator, you can put it in just like this as a fraction, or you can just do the order of operations yourself. We're going to round z-scores to the nearest hundredths place, which is 2 decimal places. So this is 0.99. This means that her score was about 1 standard deviation, and because it's positive, because it's above the mean, 1 standard deviation above the mean. It's really 0.99, okay? So it said interpret her score, so I'm going to make it into a full sentence in context. Jenny's test score was or lies about 0.99 or 1 standard deviation above the mean. Okay? So the z-score tells us about her position with respect to everyone else. She lies above the mean. She's better than the average, and specifically 1 standard deviation above the mean. Now, this ties into what we call a density curve. What we are about to do is talk about the normal curve or the bell curve. Basically, if you took a histogram like this one and you connected the top of the bars of the histogram and created a smooth curve, which we do pretty much often whenever I would do skewed right, skewed left, I would always make a curve even if it looked like a histogram or a dot plot, I would make it into a curve, right? So it's basically an idealized description of what the shape of the curve looks like. This is called a density curve. Ideally, all the bars are going to be under this curve, so the percent of total percent of all the scores under the curve is going to equal 100% or one whole. Okay, 100% of the observations are located here. Everybody should be under the curve. So if I want to find the percent of scores under the curve, above or below something, I can do that. Okay, now a bell curve or a normal curve is going to be what we're going to be spotlighting in this chapter. So here are some characteristics of this bell curve or the normal distribution. Number one, it's symmetric. You guys see these are all looking symmetric. It has a single peak. That's called unimodal. A single peak, right? And it is bell shaped. Looks like a bell, right? Now, because it is symmetric, the mean and the median are equal to each other, and they're both located in the center. So this is the symbol mu for mean, but also the median is going to be located here as well. Mean equals median because they're in the center. Mean equals median because they're in the center. And then the standard deviation basically is going to dictate how far away or how spread out the data is. So this first one here is more spread out than the second one because this is a wider standard deviation. Wider standard deviation, more spread out. Skinnier standard deviation, less spread out. Wider standard deviation, more spread out. Narrower standard deviation equals less spread out. Now we can locate the value of the standard deviation on a bell curve by thinking about where our pen is kind of taking a dip. Where our pen takes a dip is called an inflection point. And an inflection point is basically in calculus a change in the concavity of the graph. So if the graph is going from concave down to concave up, down like a frown to up like a cup, that is considered an inflection point. Down to up. So if you look here at this one, I'll do it on the other side, right where my pen makes a dip, boom, that's going to be the location of the next standard deviation. And then again here, boom, that's going to be another inflection point. So wherever your pen is taking a little dip, inflection point, inflection point. That's how you can mark off the location of that one standard deviation width. Now, down below you see what's called the bell curve, but specifically this is the normal distribution. The normal distribution is dictated by what we call the empirical rule. Another name for the empirical rule is the 68, 95, 99.7 rule. And basically this is what it says. It says if something needs to follow a normal distribution, if it is indeed normally distributed, then the mean is located in the middle, and most of the data is going to lie within one standard deviation of the mean. And I'm highlighting that here for you in yellow. So notice when I say within, I mean on either side of the mean. So one above and one below the mean, okay? If you lie between 1 and -1 with respect to your z-score, that should be about 68% of the data. So that's most people. Most normal people, there's that word normal, are going to lie in that first chunk of data around the mean, okay? They don't deviate much from the mean. As soon as you go 2 standard deviations above and below the mean, now this green, which I'll now highlight in green, you are going to be, this is going to be 95%, approximately 95% of the data between these two endpoints. 2 standard deviations above and 2 standard deviations below the mean. Meaning now you're really at most people because that's 95% of the population is going to lie between those two scores. And then if you go another standard deviation, 3 above and 3 below the mean, here, you're going to now accumulate 99.7% of the data within 3 standard deviations of the mean. So that is what the empirical rule says. This is the empirical rule. Empirical. Another name for it is the 68, 95, 99.7 rule. It says if something is normally distributed with a mean mu and a standard deviation sigma, about 68% of the scores lie between 1 standard deviation of the mean, about 95% lie within 2 standard deviations of the mean, about 99.7% of the scores lie within 3 standard deviations of the mean. If this is true or approximately true, then the data is normal or approximately normal. If it is not met, then the data is not normal. So just because you see something that looks symmetric and bell-shaped, it is not necessarily normal unless this rule is met. So I'm going to write must be met to be normal. Otherwise, don't just throw around that word normal willy-nilly. Okay, so now here we have an example. It says we have the SAT verbal test. Notice SAT verbal test is actually a standardized test. And it says that it is N, meaning normally distributed. So the first thing I want you to know is this notation means normally distributed with this and this mean the mean and the standard deviation respectively. Mean and standard deviation respectively. So this means that it is normally distributed with a mean mu of 505 and a standard deviation sigma of 110. Okay, so mean first, standard deviation second. That is the notation for normal distribution, n mu comma sigma, where mu is mean, sigma is standard deviation. How high must a student score to be in the top 10% of all students taking the SAT? Okay, we are not going to do this part yet. I am just going to set up for you the bell curve, okay? So it says state the problem and draw a picture. So the first thing you always want to do with bell curve problems is draw a bell curve and in the middle draw a line and put the mean. So the mean is 505, we're going to put it in, okay? Now let's set up by counting up and down by the standard deviation, okay? So if we were to go 1 standard deviation above and 1 standard deviation below the mean, what would that be? All right, so take out your calculator and do 1 standard deviation above the mean, 505 plus 110, and 505 minus 110. Okay, so we're going to get 395 and 615. 395 is going to be 1 standard deviation below the mean, and 615 is going to be 1 standard deviation above the mean. This means if someone scored a 615 on the SAT verbal, their z-score would be positive 1 because they lie 1 standard deviation above the mean. And if they scored 395, they would have a z-score of negative 1, meaning they would score 1 standard deviation below the mean. The percent of data that lies between the score of 395 and 615, because it's within 1 standard deviation of the mean, is 68%. Approximately 68% of people are going to score between this number and this number. So I'm going to write that down. Approximately 68% of people that year scored between 395 and 615 on the verbal SAT. Now, if I were to go another standard deviation above and below, boom, boom, I'm going to go basically 2 standard deviations above the mean and 2 standard deviations below the mean. This is going to be a z-score of positive 2 or negative 2. So I'm going to add 110 to the right, and I'm going to subtract 110 from the left. So I'm going to get 285 for negative 2 for the z-score. And then on the other side, I'm going to do 615 plus 110, and I'm going to get 725. Okay? So if you score a 725 on the verbal SAT, you're going to have a z-score of positive 2, indicating that you are 2 standard deviations above the average. And if you score a 285, you are going to be a z-score of negative 2. Now, if I highlight this middle chunk from here to here, That should be approximately 95% of the population. So I'm going to write that down. Approximately 95% of the population scored between those two scores, 285 and 725, okay? And then I could do it again for the 99.5. But basically now you guys get the idea of what the bell curve looks like and how it's distributed. So let's say I wanted to know someone who scored in the top 2.5%. This is 95% from here to here, right? So there's actually 5% left. If you do 100 minus 95, you're going to get 5% remaining on the tails, right? So 5% on the two tails, if we divide that 5% by 2, you're going to get 2.5% to the right and 2.5% to the left. So if somebody asks me, what would someone have to score to be in the top 2.5% of the population, I would tell them they would have to score a 725 or more because that's going to land them in that upper tail. And if I were to ask, what does someone have to score in the lowest 2.5% of the population, then they would score 285 or less. Okay, we're going to use this now and apply it to z-scores in class.